Every year, thousands of construction workers suffer serious head injuries, many of them fatal. In most cases, a helmet was available. In many cases, it simply was not being worn. The question is not whether we have the technology to detect this. The question is whether we are using it. Workplace safety regulations across Australia, Europe, and the United States are unambiguous. Every worker on an active construction site must wear a helmet at all times. The regulation does not say most workers. It says every worker. Any automated safety system that cannot assess each worker individually is not legally compliant. The most natural approach to this problem is image classification. Label each image as compliant or non-compliant based on what you see. But this approach has a fatal flaw. In a single image containing 10 workers, 9 wearing helmets and 1 not, a scene-level classifier will predict compliant. The violation is invisible. The alarm never sounds. Before a single model was trained, 3 falsifiable hypotheses were stated. First, a safety alarm system requires per-worker detection, not scene classification. Second, the provided academic dataset contains a visual bias that makes it unsuitable for training a production model. Third, a 2-stage pipeline using worker-level labels will achieve significantly higher no-helmet recall than image-level labels alone. Provided academic dataset contains 631 images split equally between workers with helmets and workers without. At first glance, it looks balanced, but a deeper analysis reveals a critical confound. With helmet images average 476 by 481 pixels, wide-angle construction scenes. Without helmet images average 146 by 131 pixels, close-up portrait photographs. The area difference between the two classes is 16.35 times. A naive model does not need to detect a helmet. It only needs to detect whether the image is a portrait or a landscape. Build a model that learns genuine helmet features. We need a dataset where both classes come from the same visual domain, the construction site. The Safety Helmet Detection Kaggle dataset provides exactly this. 5,000 images, all from construction sites, with Pascal VOC XML annotations marking each individual helmet, bare head, and person with a precise bounding box. The same visual domain, per object labels, the right tool for the job. 10% of SHD images contain both helmeted and non-helmeted workers in the same frame. Under naive image-level labeling, every worker in those images, compliant and non-compliant alike, would inherit the image label. This would silently mislabel 2,150 individual workers. Our centroid matching pipeline solves this. YALOV8N detects each person. Each detected bounding box centroid is matched to the nearest annotation box from the XML file. Each worker receives their own individually verified label. The complete system operates in 2 stages. In Stage 1, a pre-trained YALOV8N model scans the full construction site image and draws a bounding box around every detected person. In Stage 2, each person crop is resized to 224 by 224 pixels and passed to a fine-tuned MoyleNet v2 classifier, which outputs a probability of helmet compliance. If any single worker in the image is classified as non-compliant, the safety alarm is triggered immediately. Running YALOV8N across all 5,000 SHD images produced 18,482 individual worker crops, a 3.7 times expansion of the original dataset. 13,638 crops were classified as wearing a helmet. 4,582 crops were classified as not wearing a helmet. 86.4% of all crops received individually verified centroid match labels. The remaining 12.2% received image-level fallback labels, where YOLO detection confidence was insufficient. These 18,482 crops, not the original 5,000 images, became the training data for the MoyleNet v2 classifier. The baseline model uses MoyleNet v2 pre-trained on ImageNet as a frozen feature extractor. A global average pooling layer reduces the feature maps, followed by a 64-unit dense layer and a sigmoid output neuron, trained for 20 epochs with class-weighted loss to address the 10.9 to 1 class imbalance. The baseline achieved 83% accuracy and a macro F1 of 0.79, with a without helmet recall of 0.75. A solid starting point, but not yet at the 0.8 recall threshold required for safety-critical deployment. 3 improvement experiments were run systematically. Experiment 2 added data augmentation, rotation, zoom, brightness variation, and horizontal flipping with early stopping. Experiment 3 replaced Atom with SGD plus Nesterov momentum, added dropout and L2 regularization. Experiment 4 unfroze the last 30 layers of MoILnet v2 for partial fine-tuning with a reduced learning rate of 0.0001. Each experiment targeted the same weakness, improving recall for the no-helmet minority class. Experiment 4, partial fine-tuning, is the best model. By unfreezing the last 30 layers of MoILnet v2 and training with a low learning rate, the model adapted its deep feature representations to construction site imagery rather than generic ImageNet patterns. The result, without helmet recall, jumped from 0.75 to 0.89, exceeding the 0.8 safety threshold for the first time. Macro F1 reached 0.84. This is the model deployed for all subsequent evaluation. The ultimate test of a model is how it performs on data it has never seen before. The provided 631 image academic dataset, never used for training, never used for validation, was used as an independent out-of-distribution test set. The Experiment 4 model achieved 88.8% accuracy and a macro F1 of 0.8869. This is not only above the 0.8 threshold, it actually exceeds the performance on the SHD test set by 4.7 percentage points. The model learned real helmet features. All three hypotheses are confirmed. H1, the safety alarm hypothesis, is confirmed. 501 mixed scene images with 2,150 individual violations prove that scene-level classification is structurally inadequate. H2, the dataset quality hypothesis, is confirmed. The SHD-trained model's 88.8% cross-dataset accuracy proves it learned helmet features, not scene shortcuts. H3, the pipeline architecture hypothesis, is confirmed. The recall progression from 0.68 to 0.89 demonstrates the measurable benefit of worker-level labels and fine-tuning. The two-stage pipeline demonstrated in this project achieves 89% no-helmet recall and is a strong proof of concept. But the industrial standard as of March 2026 is a single fine-tuned YOLO model with dedicated classes for helmet, head, and person. This end-to-end approach eliminates the compounding error risk of two separate models, reduces inference time from 150 to 300 milliseconds per frame to 80 to 120 milliseconds, and pushes no-helmet recall to approximately 93 to 96%. The SHD dataset already contains the annotations needed. The upgrade path is a 45-minute training run on a free Colab GPU. Single head injury fatality on a construction site costs between 5 and 10 million Australian dollars in direct costs alone. Manual safety supervision is periodic and coverage limited. The system provides continuous 24/7 monitoring of every camera-visible worker, triggers an alarm within 200 milliseconds of a violation, and generates an automated regulatory-compliant audit log. At scale, it is not just a safety tool. It is a legal liability reduction system, a regulatory compliance platform, and an operational efficiency multiplier. This project delivered a complete construction site helmet compliance system. 18,482 worker crops were generated from 5,000 SHD images. 4 models were trained and benchmarked. The best model, Experiment 4 partial fine-tuning, achieved 86.8% accuracy and 0.89 no-helmet recall on the internal test set, and 88.8% accuracy with macro F1 of 0.8869 on 631 completely unseen images. All 3 hypotheses were confirmed. The upgrade path to end-to-end YOLO production deployment is fully documented. Project submitted by Shadi Syed on March 2026, part of the Visan Bridge course for Data Science Masters of Deakin University. Thank you.